Okay, thank you. So as Jeremy said, what I will be describing today is how to implement one form of control flow integrity type system if your hardware, well, I guess if your hardware uses the same thing. While this may not generally be applicable to all architectures, I'm hoping you'll get a good feeling for if you want to implement specific hardware features, the places in the compiler that the places in the compiler that you want to poke to achieve what you want. So first, to set some context, compiling for security is becoming increasingly important over time. Now, traditionally, we've had optimization criteria of code size or execution performance, or striking a balance between the two, or more recently, over the past few years, energy has always also become more important, which is something we described a few years ago. But security is becoming, as I say, more and more important. And the way that the way compilers can help you is in generally one of two forms. The first is finding bugs through things like address sanitizer, memory sanitizer. You turn on specific specific compiler flags, and it bakes in new functionality. And if you're doing something that you shouldn't, your program will stop and scream at you and tell you, you have a bug, I'm not going to let you continue. Please stop now. And sort of adjacent to this are research programs such as the Leakage-aware design automation project, which aims to stick more compiler warnings or extend static analysis to give you more compile time information, such as what you're doing here is probably leaking information you don't particularly care about. Now, most of these things are generic. They apply to to almost all architectures. But there's sort of a third category, which is if you have an architecture with specific hardware features designed to stop people doing things they shouldn't to your program, then you probably also want compiler support for these. And this is the thing that I'm going to be describing today. Now, overall, what I'm going to be describing is one particular hardware implementation we've had to implement for an out-of-tree backend we've been working on, and various layers within the compiler that you may want to modify to help you get the information you want. So the specific example is we want to verify instruction integrity at runtime. So this is more than the traditional, I have cryptographically signed a blob and then I stick it in memory and I trust that the blob is the same as I execute through it. You want to know at runtime if someone has pointed a laser at your memory and managed to flip a bit. You also want to make sure that calls and branches only go to known places. This is, I guess, in some regards, trying to avoid things like return-oriented programming. And yeah, making sure that while a call can generally go to any address in memory, you want to make sure that this call instruction will only ever go to the one or two places in code that you would expect. And the ideal aim of this is that if either of these are violated, then the hardware should stop as soon as possible. And the context I'm thinking of here is in the deeply embedded space. So essentially, if you were to go try and execute an instruction you shouldn't, then some interrupt would occur. So the specific example is through some clever encoding of instructions, where essentially each instruction becomes dependent on the instruction that has come before it. So say we have an instruction I and some internal state of our hardware. We can produce an encoded instruction E and some new output state. So this and R0, R1, which may have some encoding, goes through some function in the compiler and produces some output. And then this here, OXBeef, is what appears in your binary. Now, at runtime, assuming the encoding function is reversible, it can take this information and reproduce the original instruction given the same input state. So OXBeef would become add. So that is how one instruction would behave. Now, at its simplest, if you were to take, here's an example function that just does some things to a couple of incoming variables. Now, this is an example of the AEP architecture, you would produce 4 instructions, one doing a left shift, one ANDing the second variable, adding the 2 together and returning. Now, if you have, using this encoding system I've just described, the first instruction, instead of being 919A4000, based on some internal state, would become, say, 00010203. You would produce a new output state, which would then encode the next instruction, which would then have a completely different encoding, and so on and so forth. Now, the important thing to note here is that if I was then to jump from the first instruction to the third and try and bypass the second one, I wouldn't execute the instruction I was expecting. Now, depending on the encoding space of your architecture, you can detect this and stop execution before something bad happens. So this system works quite well for a single basic block. But say we have something more complicated, such as a select instruction, where the code you may traditionally generate is, I will move one value into a register, and then depending on some comparison, I'll override that with the original. Now this works quite fine for the first couple of instructions because it's in a single basic block. And in some regards, the third instruction is just the same. It's a continuation. But then we have this slight issue about the fourth instruction, because you can get to this instruction either if you don't take this branch, in which case it's just the same as straight linear code. But if you do take the branch, then the internal state from the second instruction must also somehow encode to the same fourth encoding. Now, for a couple of cases, this may be solvable in this case, but if you have a basic block with many direct predecessors, you could easily get a set of equations that is just impossible to solve. Now, the way that this hardware solves this problem is by sticking in what's called a correction value, which essentially overrides that internal state. So using this, the instruction 4 is encoded the same way. But if the branch in the second instruction is taken, then instead of using the normal state that we would get here, we would just use this value that we stuck in the instruction stream, use this value that we stuck in the instruction stream and get the same value. Now, function calls are easy because for all intents and purposes, we can just treat this as a single basic block, because as soon as this function returns, you would have the same values if you'd never taken this call. So given this system, you may wonder, why does the compiler need to know any of this? Because we could just resolve this normally at compile time. There's nothing special here. The issue is that what I've described works very well if you have a single compilation unit, but then you suddenly start adding calls from one function in one compilation unit to those in another, and you suddenly need to start keeping track of what functions call other functions. Now, this is really what this talk is about, is how you take this call graph and stick it into your object files such that you can read it back later and do some post-processing. So the first thing that we had to decide when implementing this is how do you expose this information to a user? Sorry, let me rephrase that. How do you expose this functionality to a user? Now, typically there are two ways of adding optional functionality to a C compiler. The first one is add a compilation flag. Say I add to clang -m encode instructions. Now, this works. It has the benefit of it's easy to enable. You can just add flags to a build system. That's, very simple. And it enables this for every function in your compilation unit. The downside is, because we need to stick these values in various places, and especially around calls, we sort of have an ABI break here, which results in us needing to make sure that a user uses this flag across all functions within their entire project, not just a single compilation unit. Secondly, as a compiler flag, it really only affects C. If you are doing any handwritten assembly that isn't in, say, an inline assembly block, you would need to understand this system and patch it yourself. And thirdly, there are some concerns you could have about code size if you're just adding these extra instructions all over the place. And in a deeply embedded environment where code size is the critical thing, sometimes you don't care how long your program takes to run, you just care that it fits on your chip. Perhaps you don't want to start adding an extra word to your code size every 6 or 7 instructions. So, and in the end, we decided not to do this. What we've done instead is add an attribute to clang, which enables this on a per function granularity. This has a lower cost overhead for sort of non-secure functions, i.e. 0, we're not changing them at all. And we have a much greater control over which functions we change the ABI for. It still has the same downsides of it still only affects C, and we need to make sure that a user uses the right flag all over the place. So say you want to add such a attribute to clang. How would you do this? Now, there are a few things that you would have to change. The first thing is you would need to decide what kind of attribute you want to add. Now, for our purposes, this, whether something is secure or not, is a type attribute. It fundamentally changes the type of something that you have. You now have secure functions and not secure functions. They are different things. This allows us to add error checking because if you start having function pointers, you need to know whether you need to treat this thing as a secure object or not. And the function things that we've had to change in Clang is there's a class called function type that contains bits, such as whether the function is const. And we've had to extend this for having a bit to say whether this is secure. And this enables the error checking and also allows us to generate IR later on. More specifically, this, for calls, we have this extinfo which has the same thing. So we have a bit here that allows the call site to know whether it is calling something secure or not. Now this is helpful for if you have a function declared that you haven't yet defined in this compilation unit. You can set this when this bit is set, we know whether the function being called is secure or not. I want to make a slight distinction here that this is not quite the same as having a different calling convention. This is one approach that you could use for adding such things, but for our purposes, we haven't used a calling convention because our target already makes use of various calling conventions, and we want to be able to turn this system on and off independent of that and having calling convention fast underscore with underscore secure just becomes slightly painful. And when we get down to the Clang code gen, we essentially read this bit and map it down to a LLVM function attribute that's just the string protected. So that's how most functions work. The slight issue we have with such a system is function pointers present a challenge, as they generally do for a lot of things. In our case, now that we need to know what call site will call what function, we can no longer just have function pointers being able to call anything because of this need for an initial state for the first encoding of an instruction. There are a couple of solutions for this. If your hardware generates this initial value based on the address of a function, all is well. We can just continue. Function pointers are nice and easy. Otherwise, we need to calculate this. One approach could be we could use the same initial state for each function, but that defeats the purpose of having such a system. If suddenly you can call everything again, then why did we bother? We could calculate all possible core targets. Maybe. I mean, generally not, because the chances of your function pointer only ever calling functions in the same compilation unit is rare. Even under LTO, if you have just a single function in assembly, that would defeat the whole thing. And what we decided to do in the end is use the fact that, well, a user will know what functions they want to call. They're writing them. So what we've ended up doing is extending our attribute to just add some string. Now, what this string becomes is a function group identifier, whereby a function pointer with the attribute protected my function can now call any function that has been declared protected my function. And we can extend the extinfo and function type stuff as I described on the previous slide to add more error checking for functions that are in one group, function pointers in one group trying to call function pointers in another, because we know that's not going to work. So that's really all of Clang. Now for LLVM, like the core middle end of LLVM, really for such a system, we don't really have to change anything. As long as this attribute is makes its way through to the back end, we can just leave the optimizer to do its thing. With one small example. We want to stop the inliner from taking our function that we've said we care about, and we want this to be secure, and inline it into something that's not secure. Because now we think we've made this thing nice and secure, we haven't. So we've had to change the inliner to look at this attribute, and if the protected function attribute is there, then immediately not consider inlining this function into any of its call sites. We've also made the decision that the other way is generally safe. By generally, I mean any case that doesn't use inline assembly. If you have an inline assembly instruction, we go down the safe route and just go, okay, right, I'm not going to risk touching this and breaking your code. And that is the middle end for such a thing. Now, for the back end, we need to change a couple of things. While we have this this attribute when we have the LLVM instruction, we need this information to survive through instruction selection and all the way to instruction emission. Now, the route that we've taken for this is a bit different. What we've done is we've taken all our call instructions to accept a hidden operand, which is this 64-bit flags field, where at the moment we use 17 bits, one for whether the call is to be regarded as secure, and we hash the string, the user-provided string, and turn that into a 16-bit field and stick this in this flags field. And then instruction selection just continues as normal. So once we've selected instructions, register allocation, and all the normal fun stuff you would do in the back end is just continues as normal, because you don't need to make any special considerations, because this is just some operand to your call instructions. So then comes to the end of the back end, and the real aim of what we're trying to do here is we want to note down the control flow in our binary so we can calculate all these values later. Now, this for us is split up into two parts. Right, just before we hit the instruction printer, we have a very late pass that we've called our security analysis pass. Now, what this does is prepares a function to have this metadata annotated within it, which essentially consists of storing some data in the machine function as to what instructions, which calls are secure or not, and also where we have these locations that we need to fit in correction values, we just stick in a NOP that we can override later on. And yeah, so this pass builds lists of branches, calls, jump tables, anything that could affect control flow that I need to know about to encode my function. And also generates me a small statistics report so I know that how big my code has got as a result of turning this on, as opposed to any regression in instruction selection, for instance. So now that I have this information, how do I encode this into a binary? Now, what I particularly wanted was something that I can stick into an object file and easily read it out later. I don't want to have to worry about telling the linker anything special. So what I've gone down is just a simple serialization format, whereby if I have the start of a function, I stick into a section a value 1, the start address, and the group of the function. For the end of the function, I do the same thing. And for calls, I encode for direct calls, I encode the call site and the call target. And so on and so forth. I have something similar for jump tables, which has a count of the number, how big the table is, and all the destinations. And through this, you serialize your entire control flow into something which you can just read out later on. The linker can just append one compilation unit to another. How we've implemented this in LLVM is we've reused, there's this class called assembler printer handler, which typically is private to the instruction printer, but can sometimes be useful for any target-specific weirdness they want to add to an assembly. So what this, to assembly output and object output. So what this does is it gives you a few hooks, which we use for adding labels that we can refer to in our metadata later on. Now, so this gives us hooks like, I'm about to start emitting this instruction. Do you want to stick any labels in beforehand? I've just finished this instruction. Is there anything you want to do? Begin function, end function, and so on and so forth. Now, this is used for adding, this is used normally by LLVM to add some kind of debug information, but we're just reusing this for our purpose. So by the time this is completed, we've emitted an object or assembly file, and it has this debug secure section at the end that holds the control flow of our function. So now we've got to this stage, how do I use this information to make this hardware do its thing? So what I have here is a copy of LLVM objdump, because this reads in object files and disassembles them. And the first thing I do is I read in all this metadata, and I create in memory the control flow graph of all secure functions. So I know the internals of all the functions, which non-secure functions call secure functions, and so on. What I then do is I then assign this initial state 0 to all functions, and one at a time I just encode each basic block as I described earlier, noting the state of each relocation, where relocation here is anywhere where I need to stick a value somewhere else. I then do some sanity checking that I have actually understood the entire program, fill in all the gaps, and then write this object file back out. And the end result is I can take a function. This is my example from one of the early slides, and I have encoded all instructions. Actually, I have a better demonstration. If this. So a small example here of main calling bar. Bar is marked as needing this secure system, and bar just returns 2. So if I build this, and then encode it, it's not called encode. So my tool has a lot of verbose output for telling you what each instruction is. And then, what am I? Right, I can output my instructions. So what you can see here is the instructions that have extra hex in square brackets are encoded, and this prints the internal state of this hardware state machine. And to show that something is really being done, I can show you the real instructions, which the disassembler doesn't actually know what the encodings are. And you can see here that the encodings in my object file are very different from the encodings in the real instructions, which the hardware will eventually execute. And then with this, and then you can stick this object file into your machine, and it executes as normal, having been able to decode these instructions to bring back the originals. And that is my talk. Does anyone have any questions? I don't particularly have an attack in mind. This is more one of our customers came to us and said, we have this, Jeremy, the microphone is probably muted over there where there's no one to unmute it. So basically I was given, we have this nice hardware feature that can encode instructions, and we really think the compiler should be able to use it. Go make the compiler use it.
So is the embedding of the correction values when you embed one bit embedded in there, it basically subverts any sort of protection that you want. Like you could overwrite something before that, correct?
So the question is, if I replace the correction value, would that subvert the protection? No, I don't think so. So the correction values are mandated by hardware because it understands that the branches need to override this state. And I can't think of a more detailed answer than no at the minute. Okay.
Thank you very much.
Thank you.